Welcome all of you to session 5. I hope you can see the screen now. So in this session, we are going to go deeper into the details of pipeline structure. One second. Let me reduce that. Okay. So understanding what is happening in today's class is very important for you to follow the remaining sessions. So please stop me if you don't understand something so that I can explain again. Okay, so let us, as usual, start with some quiz on what we covered yesterday. So I will be initiating a poll. Please try to answer. Basically, it is the questions are based on the session after the break yesterday. Okay, I explained something about pipeline. I'm going to ask you what do you understand so far, so that I know where we stand, and then we can start from there. Okay. So let me start the first question, and we will have a break somewhere around 1 hour after the class. No, mostly we will be here, so we'll have a break at that time. Okay, so before I start, let me just quickly give a recap so that you are all ready for answering the questions. Okay, so we are going to study about pipeline, and we saw that processing of instructions takes many steps. Some of them are: first we have to fetch the instruction from the memory and then load it into instruction register, so that the instruction with the opcode and operands, they come into the CPU. Okay, right now the instructions are residing in the main memory on the code part of it, and then when you access it, when the CPU accesses the memory, it comes to the cache, and we assume here the code is available already in the cache, so that when the first instruction fetch happens, within the cycle, the opcode along with the operands come into the CPU. So it takes only one cycle. Remember one thing, accessing real main memory will not be done in one cycle. So if you are assuming that it is one cycle, it means that it is coming from the internal code cache. So our CPU has code cache and data cache. This I told you many times. So let me restate that. So the code comes here. Though it is saying instruction memory, our description always it says instruction memory. It will not say cache. But the fact that it is done in a single cycle, it is coming from cache. Okay. So some of the things you have to understand it. It may be mentioning memory. It doesn't mean that it is always coming from memory. So after the instruction is fetched, it should be passed on to the next stage, so that during the next cycle, this particular module start fetching the next instruction. Okay, subsequent instruction, because it is starting off from the next cycle itself. It is not waiting for this earlier instruction which was fetched to be executed completely for fetching the next one. That is the unpipelined structure. This is a pipeline structure. Instruction is fetched every cycle. So first instruction is fetched, it is passed on to this. I will talk about how it is passed on. Then it is decoded, and once you decode, you know what is the type of instruction, what operands are needed. Then if it is required from the register, access those operands, and then both the decoding and accessing of operands are done in this stage. And once the operands are fetched, it should be fed to ALU. So imagine there are some some registers where it can be stored. Okay, the instruction operands have to be stored. The values of registers have to be stored in some other temporary registers. So they are all going to be available between the stages. I will talk about it. Anyway, yesterday, last class, I didn't talk about that. So somehow the operands are passed to ALU, and information about the instruction, whether it is an add instruction, multiply instruction, is also passed across. remember, while the first instruction what was fetched is here, there is one more third instruction is getting fetched here. Second instruction is fetching the operands for it, whereas the first instruction which was fetched is getting executed here. So imagine that different instructions are operated on by different stages during the same cycle. So this is a timeline. The instruction is moving into the pipeline. Different operations happen. So operands are operated on, maybe add or subtract. Result is found. That result is now passed on to the next stage. Now, if it involves some memory access, it will be done. Otherwise, memory will not be accessed. It is not that every instruction that is going through will need a memory access, but there will be a time lag of 1 clock here, even if an instruction does not need to access the memory. The reason is, suppose, imagine an add instruction is moving in, it has found the result of add, but it doesn't need to access the memory now. It is result is loaded into the register only, but you cannot say that I don't need to access the memory, so I want to directly move to this section, this stage, so that I can save one cycle. It is not possible because already there will be another earlier instruction in the stage. You cannot have more than one instruction in every stage. So since the instructions are coming one after the other, there is already one instruction, earlier instruction, may be doing a register access. So you cannot have this instruction also to move the stage. So they have to wait. Nobody can just cross or overtake some other instruction earlier to it. Okay. So I hope this is clear. The result is written into the register set here, right back, and then it goes out. That means the instruction execution is completed. So this is what is happening in a pipeline. So now you are all ready for answering the questions. Even if you don't understand fully, please try to answer them, because I will know how much to explain, where to explain. So don't hesitate. I don't know the answer, so let me keep quiet. Okay. Okay. Let me tell you, these questions are not easy, little bit difficult. First two questions are single choice, and the remaining three questions are multi-choice. So multiple choices are there. Anyway, it will come up when you are seeing the question. Now, first question, please read it. Okay, I hope all of you are ready. This is a single choice question. I am initiating the poll. Okay, while you are answering, let me help you. Here we are assuming a risk pipeline. If you see the instruct, it is mentioned here, and then it is a 32-bit. Okay, maybe I should have mentioned that also. It's a 32-bit risk pipeline. The instruction width is 4 bytes. Okay, please keep it in mind. I know some of you answered, cannot undo it, but it's okay. Should I wait? Are you going to answer, or you decided not to answer? Okay, good. 40 people out of 48. Very good. 43, 44 out of 48. Still 4 people are thinking. Okay, so let me, I am getting 46 now. Fine. I am going to end the poll and share the results first. Okay. Okay. So the result says the distribution is all over. I don't know. Based on this, what did you conclude? Don't go by majority. Okay. Let me explain. Or sorry, I'll show the answer and then explain you, because it will make you think. Okay. I hope these two you are aware. So five people are correct. Five of you are correct. So let me stop this sharing. Okay, let me explain. This is the instruction fetch cycle. That means, let us go by one. It initiates a write access to the instruction memory. If you look at the write access itself, you know that CPU will not try to write into the instruction memory. So I don't want you to choose A. I saw some people still saying A. Maybe negative marks for A, because you cannot access instruction memory for write purpose. So it is not correct. Second, it initiates a read access, very good, to IM, that is also correct, but to the address pointed to by PC plus 4. Remember, during this cycle, whatever program counter is pointing at is accessed, not the PC plus 4. Okay. Currently, whatever is the address pointed to by PC is accessed during this cycle. And then post increment, it is not a pre increment, it is PC plus plus. That means after accessing the instruction at the location PC, it is incremented by 4 and stored back into PC, so that in the next cycle it is ready to access the next instruction. Now the question is, why is it incrementing by 4? It is not PC plus plus, it is not increment by 1. The scalar value is 4. Okay. If I say even plus plus, it is a 4 pointer. It is a pointer of scalar size 4 bytes. So it is trying to access the next instruction in the next cycle. So it is preparing the PC to point to the next instruction. So it will not be accessed in the current cycle. So it is not plus 4. So it is wrong. Now PC is incremented by 1. That is wrong, because as I told you, it is not accessing it byte by byte. It is accessing 4 bytes. It is accessing. It is not a character pointer. It's a pointer to instructions which are 4 bytes wide. So incrementing by 1 will not make the PC ready for next access. Okay. So it is also wrong. Now what is it D saying? Incrementing of PC by 4 is done by a dedicated adder circuit during IF itself. See, I mentioned it. Some of you might have noticed it. So at least 3 people were aware of it. Increment by 4 is correct. And then a dedicated adder circuit is required, because this ALU cannot be used. Because while PC is incremented by the hardware in the IF stage, this is being used by earlier instruction. So you cannot use the same ALU for the PC with 4. It has to be done in a separate adder circuit, which is done and within IF, instruction fetch itself. So after all the statements, the statement 4 is the right one. All other things are wrong. So you get it wrong, don't feel bad, because you are learning now. I intentionally made it tough so that I can explain the concepts while I am solving this question, so that I don't have to spend again on this thing. So it is worthwhile. Even if you have thought about it and then made something wrong, you will understand what went wrong, so that it will be clear to you, then rather than me explaining without even making you think. So that's the intent. So don't feel bad if you are getting all 5 wrong answers. No issues. Okay. As long as you understand my explanation. If you don't follow my explanation after this, no, if you are not convinced that D is the right answer, you should ask me. Okay, fine. Next, this is also a single choice question. Please think about it. It is about instruction decode stage. Okay, the correct choice is D. Here, you have to understand that in the decode stage, two operations are done. One is decoding of instruction fetched during the previous cycle, and then accessing the operands for that particular instruction from the register set. So it is reading the operands from the register set as well as decoding the instruction. The decoding is done first because we have to understand what is the instruction first, and then based on the instruction, if it has to access the operand, it will be fetched during the same cycle. So if you look at the options, D option only says decoding of instruction fetched during CC1, that is previous cycle compared to this, and reading its operands are also done in parallel, okay, in the same cycle. Now, why the other options are wrong? A is wrong because it says decoding of instruction to be fetched in the next cycle, okay. So, which is not possible to decode an instruction which is yet to be fetched. It is future, so it is not possible. Only decoding of instruction fetched during the previous cycle is done. Only decoding is not done because I am saying decoding and register access, operand access is done. So this is wrong for that reason. And decoding of instruction and writing into its operand is wrong because we are not writing into operands here. We are reading from the registers, those operand registers. So this is wrong for that reason. And this is wrong because incrementing of PC by 4 is wrong. It is not done here. It is only a register set is available. Adder is not here. Adder circuit is dedicated. Adder circuit is here, and we need to increment PC in this cycle itself so that the next instruction will be fetched in the next cycle. You should be ready with the new PC value, program counter value. So you cannot wait for the next stage to increment it. So that is also wrong. So D is the right answer. Okay. Now this is a multiple choice question. I will launch the poll. Please try to answer. So I don't think it should take more time. Please answer. I'm not able to make out how many of you are right. So let me show the result and see how it shows. I don't know. First time I am showing the multiple correct choice. Okay, 41 out of 51 right now. There are some people dropping off. I don't know. Okay, guys, 45 out of 52 now. I'm going to stop the polling. Maybe I need to, okay, I will share the results. I don't know, maybe there are 76, okay, it is not showing up in a multiple choice options, how many of you have chosen what combinations. So it is useless unless I look at the output. Okay, now let me show you, let me go through the statements and then see which is correct. In the execution stage, execution of instruction by ALU is done by using the operands passed by ID stage. This is what I explained in the previous question. ID is passing the operands to ALU and it is getting operated upon. So A is the right statement. Now, operation to be performed by the ALU depends on the instruction being executed. Now, what is the operation being done? It depends on the instruction being executed, because it is operating on operands is a right statement. And what is it going to do? Whether addition or subtraction or logical or AND operation depends on what operation was supposed to be done for this particular instruction. Whether it is executing add instruction or subtract instruction, based on that, that operation is done. So operation to be performed by the ALU depends on the instruction being executed. It is true. It's a correct statement. So if any of you have chosen A and B and not C also, then, okay, let me tell you whether correct or wrong. Let me see why C is correct or wrong. ALU always performs add operation irrespective of the instruction being executed, which is a totally a wrong statement. It has to perform what is supposed to be done by the instruction. You cannot say I will do always add. So it's a very stupid statement. So remove it. Because you have chosen A and B, this is wrong. So I don't know how many of you have chosen A and B. If you have chosen A and B, it is correct. Okay. So I think based on this, I'll assume that 67% have chosen both, but it is difficult to guess. Okay. Maybe. Okay, there is some question. Let me answer that. Okay, I'll stop this sharing. What is the question? Okay, let me read out the question to you so that you understand. Although I chose D, okay, I was saying, oh, sorry, it's not a doubt. Okay. Okay, see, let me try to explain the question being asked. See, someone is saying that I chose D and not A because it is not fetching the operands. Yes, you are right. It is not fetching the operands, but operands are available. Please remember, it has to do some operation. It needs operands. What I said was fetching the operand from the register set is happening here. That means, see, it's inside the register. Suppose if I am saying add R1, R2, R3, the instruction is saying that I want to add R2 and R3. So R2 and R3 are still inside the registers only. It cannot perform an add operation. Don't think that there is a hard line between them and then it can directly access from the register set. It cannot. I will tell you the reason. Though they are directly connected, during this execution, it is not accessing the operand from the register. It is not accessing it from there. It should have been accessed and available here. I will explain it in this class. Okay. It is a very simple diagram shown. We cannot show everything here because it is logically you have to think one more thing, that while this is performing an add operation or whatever, another instruction is here accessing the operand in the register set. So ALU also cannot access it from here, and then when I'm saying another instruction is accessing it, there is a two instructions cannot operate on a single block. Remember here, I will tell you where it happens, because you will see that register set is here also. But the fact that this cycle register set is not shown, that means what? It needs operand, but it is not directly taken from the register. It is somewhere passed on and then it is available in the middle. Okay. So I will explain it today so you will understand it. That's why it is working on the operand is a write statement. It is passed by the ID stage. It is not accessing it from the register set directly. It is passed. So, and then in B, what if the instruction being decoded instead of executed? I didn't get to the, in B, what if instruction being decoded in B, what is B? Okay. B is, okay, operation to be performed by ALU depends on the instruction being executed. Okay. If I understand your question, I am the B, let me explain what is the B option talking about. It is talking about what is ALU is performing, what is ALU is doing. If you see the picture here, ALU is not appearing anywhere else other than EX stage. So I am talking about the ALU which is given here. Okay. And we are also talking about the EX cycle. Okay. That means in this cycle, one instruction is in this EX stage. Some other instruction is in ID stage. Some other instruction is in IF stage. Similarly here, I am just focusing on what is happening in this for this instruction during this cycle. Okay. So I am concentrating on what is happening during this cycle in this stage. In this stage means whatever may be the instruction here, what is happening to it and what is the operation done by the ALU on for that instruction. Okay. So the B statement, why is it correct? Let me explain. And operation to be performed by the ALU depends on the instruction being executed. So if suppose add operation was done, add operation instruction was fetched 2 cycles before, that would have come here now. 2 cycles back, I fetched add instruction, which is in the last cycle it came here, and the current cycle it is here. Remember, I am talking about the during this current cycle, an add instruction which is here is influencing the operation add on ALU. If it was subtract instruction, it will make the ALU to perform subtract operation. So the current instruction which is in this stage is influencing the operation to be performed by ALU. So I hope it is clear. Maybe you can confirm if my explanation is clear, so that I can go forward. So looks like there is confusion is there. Okay, it's a difficult concept, and as we go further, maybe you will become more and more clear rather than more and more confused. But don't worry, even if you have some doubts, it will get cleared soon. Okay. So the correct answer is A and B. Okay. Let me, ALU is also used to compute effective address. I am not going to talk about it now. You are already finding it difficult. So let me defer this note. Let me defer it. Okay. For now, don't worry about it if you don't understand it. Okay. Let me go to question 4. It is also multiple correct choices. It is also difficult. Don't worry, even if you get it wrong. So let me help you. When I say data and cache, when I put together, even though it says data memory, it is a data cache. Okay. So that it is completed in a single cycle. That's what I mean by data in bracket cache. Okay. Don't get confused. So let me launch the poll. Think about it. So it is very interesting. I am able to get the questions also and clarify it, which doesn't happen in the classes. You guys will not even open your mouth. I'm very happy. People are given up. Don't worry, try to answer. At least you should be happy if you have chosen one of the multiple correct answers. Okay. If you have chosen even not all of them, but if you have chosen one of the correct choices, you should be happy. And if you have chosen a wrong option, then it will at least clarify. My explanation will make you understand. So just try it out. Don't think that exam will be so tough like this, but here I can be asking you tough questions. That's the intent. Okay. Okay, 40 out of 51. I'm going to stop it. Please, I'm getting last minute answers. Don't worry. Answer. I will give you some more time. Very good. I'm very happy to see maximum response. Good. That's the way. Don't be afraid. Don't be afraid to make mistakes. Fantastic. I got 50 out of 51. That one person is not in front of the computer, I am sure. I will dig out this and find out who is that one person. Do you know I can actually find out? I normally don't do that. I can do it. Okay. Okay, guys. Very good. Let me share the results. Okay. So I don't know how many of you chosen what combinations. This display is not showing. Maybe I'm not able to see it. Let me explain one by one, and then sorry, I'm just doing something. Okay. I don't think you need it. Let me move it out. One second. If any of you ask questions, please, you can ask. Sorry. Okay. Let us understand. This is a memory cycle. That means what? Instructions are coming in. Okay. Different instructions are in different stages. Every cycle, after one cycle is over, a shifting happens. It's like a bit shift. When you do if you have seen a shifter, every cycle, suppose if you have seen 1 0 0 like this, and every cycle that one will be moving in. Okay. You have seen in a digital design lab, you guys have designed it. So similarly, every cycle, the instruction is moving. Okay. What was previously here comes here. Similarly, what was previously here moves here. So it's a shifting operation, shifting of instruction. Every cycle on instruction, which is in the pipeline, all of them get shifted. So somebody is here, some instruction, I am not even worried about which is instruction it is. We don't know. Some instruction is here and it is in a memory cycle now. Now, what is the operation should happen here? And based on the instruction type. Okay. Now, let us read it. Instruction memory access happens during this cycle. It is clearly shown it's a data memory. Instruction memory access is happening here only. So this statement is completely bullshit. I don't know how many selected it. I'm sorry, 25 of you have selected it. Okay, let me tell you why. I don't know why you are going wrong here. Let me explain. What is this picture shows? This picture shows an instruction in this cycle accesses instruction memory. Similarly, another instruction which is in this cycle accesses register set. So during the cycle, I am sure in parallel these are also happening. I am not saying that instruction memory is not getting accessed. It is accessed, but it is not for this cycle. Please understand. Maybe you have not understood my question. I am asking about memory cycle. That means what? Only one instruction is in the memory cycle. This instruction is in execute cycle. This is in instruction decode cycle. This is in instruction fetch cycle. All of them are there in this particular time instant. All of them are happening, but they're all happening for different instructions. My question here talks about the instruction which is in memory cycle. That means I am worried about only this particular instruction which is in this cycle, what is happening to it. So don't read me wrong that I am not making a statement that during this time instruction memory is not accessed. I'm not making a statement like that. It is getting accessed for different instruction. It is not for this instruction. So all the modules are busy doing something. I am only asking you what is happening here. See, let me explain you one more thing. At this moment, you guys, ECE guys are sitting in this class. At the same time, CSE guys are sitting in some other class. If I ask you a question, during the ECE cycle, software testing course is getting conducted. If I say it is not correct, during the CSE cycle it is happening, not during the ECE cycle. So, but they are happening parallelly, but different instruction, different set of instructions. The CSE guys are sitting in that class and you are here. So when I say instruction memory is getting accessed during this cycle, I am saying during this memory cycle. So it is not correct. Okay. So maybe some of you might have mistook it. It's okay. I hope now you are clear. Maybe you are not understood my question. Fine. Now B, read access to data cache memory happens if the current instruction is in CC4 is a load. Now, if there is a load instruction, load means what? Loading what is in the memory into a register. Store means what is in the register getting written into memory. Now, you know that this instruction is accessing the data memory. That means what? This data memory access will happen if the current instruction in this stage is either a load or a store. Now, if it was load, suppose a load instruction was accessed earlier and it has come to this stage, that load instruction needs to access the data memory, get the some content of some address so that it can write into the register after reading from the memory, because it is loading into register. But before loading into register, it has to access from the memory. This is memory. You are reading the content and then going to write into register. So writing is going to happen here, but you have to perform the read from the memory here. So if it is a load instruction here, it will read from the memory now. And when that instruction moves to this cycle in the next stage, in the next cycle, the actual writing into the register will happen. Reading is happening here. Writing will happen next cycle. Writing into the register happens in the next cycle. So that is for a load instruction. Now suppose a store instruction is in this stage. That means what? You are trying to execute an instruction which is a store. That means it is trying to store a register value into a memory. So in the whole pipeline, this is the cycle you can access the data memory. Okay. When the instruction, store instruction is here, it is it should perform a write operation into a data memory. Now, which register it has to store is decided here and then passed across to this. Okay. So a write operation, a write access to data cache memory or data cache memory happens if the current instruction in CC4, okay, is a store instruction. So B is correct, C is correct. Okay, let me see whether any other things are correct. If the current instruction is an arithmetic type, that means if this instruction in the memory cycle is a arithmetic instruction, add instruction was coming, add operation was performed here. Now the result is available, but it cannot be written into data memory. It has to be written into a register. So it has to wait. So it will pass through this. Okay. The register result, whatever was computed here, add operation, will be passed down to the write back stage. So there is nothing to do with the data memory, because when add instruction is getting executed, you don't need to do anything with the data memory. So if the current instruction is an arithmetic type, no data access happens. So this is also correct answer. This is of course wrong. So if any of you have selected BCD, you can pat your back. Okay. Now there are no doubts here. So that means either those who have made wrong answers, wrong choices, have understood it. I am losing all 1 hour here. Okay, no problem. You are getting ready for the next one. Okay, fine. Let me ask you the last question. Multiple choice again. Please go through it. Don't take too much time. As you read a statement, if you feel it is correct, choose it. Okay. It is not an examination. You don't have to be correct always. You can be wrong, no issues. What you get in your mind by reading the sentence, go by that. Okay. Don't spend too much time. I cannot waste too much time waiting for your response. It is taking a lot of time. I'm going to wait very less time now. Okay. Quickly do it. I will give you another 10 seconds. I want to see how you respond when you are in pressure. Okay, no problem. 30 I have responded. I am going to, sorry, I am going to end it. When you are getting into the bus, I am taking off the bus. You will curse the driver. I don't want to do that. You are still selecting. Okay, I am going to stop, guys. Let me share. Okay, let me explain quickly. It's a right back. That means what? If there was an instruction in the previous cycle, that same instruction which has come now, okay, was a arithmetic operation. Okay, let me not explain it that way. Sorry, I'll restart again. So you are having one instruction here. Okay, assume it was an arithmetic operation. That means add R1, R2, R3. If that is the case, add operation was performed here and its operands were fetched here, and that result what was computed was passed through this like this, and it is available now. I can write the destination register here. Okay, that is what will happen. Okay, now suppose that was for the case of add or some arithmetic operation. Suppose there was a load instruction currently here. What does it mean? The load instruction is trying to load from memory into some register. Now that memory access would have happened here. Whatever is the address at which it has to be read from was computed here, maybe indexed addressing or whatever, it was computed here, and actual content from data memory is fetched here. Now loading into a register happens here. So writing into register happens and it is into register set. Now what are the instructions may not influence this, nothing will happen for some instruction. What are they? Suppose it was a store. It was a store operation. If store operation was coming and it is here, store is doing what? It is trying to store some value from the register into a memory. That register was accessed here and stored into the memory during this cycle. It has nothing to do here. It has stored the result. A store operation is writing into a memory which has happened here. So it doesn't have to do anything here. So it will not do anything. So arithmetic operation may do something, load operation may do something, store operation doesn't have to do something in this cycle. Okay. Now let us look at the answer. Writing back the result into data memory happens. Now I am saying writing back the result into data memory. There is no data memory here at all. Only register is there. So it is outright wrong. Okay. Writing back the result into instruction memory. Instruction memory is accessed only here, nowhere else. Please remember, during this cycle, instruction memory is not accessed. So it is not happening here. Now writing back the result into register set happens based on the type of instruction. That is very important. If it is an add or something, then it happens, and register set access is happening during this cycle. So this is the right answer. Now, if the current instruction is a load, the value read from the data memory during the previous cycle is written into register set, which I explained to you now. So load will have an influence because the result has been read from the memory, but it has not gone into register set. So it has to happen here. So D is the right answer. Now, what about this? If the current instruction is a store, if it was a store instruction, the value to be stored is read from the register set. It is too late. If the store instruction has come here, that means the store operation should have happened here. Now we cannot say I am going to read the register for the store operation, which is supposed to be done in the data memory access. So E is totally wrong. You cannot say E is correct. So of course F is wrong. So C and D are the right answers. I don't know how many of you did that. So let me show the answer. Stop sharing. Now, okay, I didn't share the result to you. Sorry. This is the answer people have given. There are wrong choices made by some, but don't worry. I hope you got that right now, clearly. Now, guys, what is the time? Almost on 1 hour now. I am just going very late. No problem. I am going to break now. Do you need a break now or not? Sorry?
Yes.
Yes.
Yes, yes.
Okay.
Yes.
Is it clear so far, whatever I explained? Once again, I will put you all in a... I'm not able to... Okay, 1 second. I will... Hello, welcome back. Okay, so we saw in the quiz now how different instructions go through that, and then I deferred some implementation details so far. So some doubts may be lingering in your minds. I'm saying some things are happening, but I'm not showing you how it is happening. So I'm going to spend some time on explaining how things happen so that any doubts that you have based on the discussion so far, they will get addressed. The important thing that we are going to talk about is pipeline registers, okay, and then little bit high level pipeline structure. I'm not even going into the implementation fully because it will be very complex. Okay. One thing is I'm talking about 32-bit RISC processor. Okay. That's our, always assume that that is what we are assuming. Now, I'm just going to give you instruction format because this understanding is little bit required to get an idea how the pipeline works. So when I say that 4 bytes or a 32-bit an instruction is read from the instruction memory, it is structured like this. First, every processor may have different structure. I'm not saying that this is what is going to be followed by every processor. ARM will have different, Intel will have something else. Don't worry about which processor. Actually, it is MIPS here, but you don't have to memorize it. I am explaining it only for clarity and understanding. So when you read an instruction, it is binary values of 32-bit binary value. It is reading. The processor is reading just 32-bit of values. Based on that, it is going to understand what is the instruction it is supposed to execute. So the operation to be performed is available here, and then two operands. Okay, which are the registers? If suppose a processor has 32 registers, R0 to R31, those values means if it is 001, it means R1. The first operand is R1. If it is R2, it is 002 means the operand is first operand is R2. And if this value is 3, that means the second operand is R3. And destination is some value 4. If it is having a value of 4, then it is the R4. So the bit pattern exactly mention which are the registers being accessed. There are 5 bits reserved for this. Okay, then you will know that maximum we can represent 0 to 31. So if your register set is 32 registers, R0 to R31 or R1 to R30, whatever may be. So those register values can be mentioned here, which are those two operands and which is the destination register where the result has to be returned. And what operation to be performed is available here in this first 6 bits. And then there is some constant values. Okay, if this, I'm talking about this instruction format. Okay, this is about any arithmetic operations. And you might have heard, you might have seen ARM instructions also. There is some shift bit, number of bits to be shifted. You can give it along with the instruction. Okay, so that value what you give in the instruction is stored here. Similarly, there is something else which you don't have to worry about. Okay, it is depends on what is the arithmetic operation or logical operation and what are the operands. And if you have to do any shift operation along with the add operation, if you shift it and add, then how many bits to be shifted is mentioned here. This 5 bits are reserved for that. It is about R, any register operands related instructions. Now what about immediate constant? You might have seen some instructions, MVN, move, negate some register R1, okay, and then constant hash some 4. Okay, that means immediate constant is some value you pass along with the instruction and say that that should be negated and then loaded into register. If you remember MVN instruction, we might have seen in ARM. Even if you don't remember, instructions with some immediate constants coming are categorized like this, and they are format like this. Okay, and you may have a transfer, jump on, offset, some jump to some offset. That means you jump on carry to loop. Loop is a label which is saying that from the current PC value, jump to some loop label which is in the memory. So you are supposed to, after this instruction is executed, if carry bit is set, this processor will jump to the address loop. Now what is loop? This is some offset value, okay, which is passed along with the instruction. So this offset, it could be plus or minus something. In this case, this is the current instruction, and then the flow is supposed to move to some other instruction in loop, which is maybe 10 bytes earlier. That means minus 10 will be stored here. From the current PC value, you have to subtract 10 so that PC is loaded with a new value. So PC will be modified so that after the jump on carry instruction, if carry bit is set, then it will move to some other location. Otherwise, it will continue. If the carry bit is not set, it will continue with the instruction. So if you want to understand this, you have to have a clear idea of what are the assembly instructions, what they do. Okay, that is required. So there is immediate constant you may have, or jump to some other value. This is transfer, immediate constant transfer or a branch, also is coming under this category, and then jump instructions coming here category. So this is the format in which those bits are organized. So I hope you follow what I'm saying. Different instructions based on whether it is a arithmetic operation or any branch instruction, or is it a jump instruction, they are categorized. The bit patterns are understood by the decode logic following this convention. Okay, the instruction decodes these values based on what is the instruction type. If you remember in networking, based on the header value, whether it is a TCP packet or UDP packet, the rest of the data will be processed. Similarly, instructions are also processed based on what is the opcode. If it is an add instruction, it will know that the format is like this. If it is a jump instruction, then if this number is something specific, it will take that this whole thing is a target address offset. Okay, so is a total address. It is supposed to move to this address. So instructions are decoded, understood based on these values. That's all. Okay, don't worry too much. I will explain it as we go further. Okay, these are all some different operands and destination register, shift constant. I already explained to you. So instructions are encoded in binary. They are 32 bits long. There are 3 instruction categories. R format is most common. I format and J format are different, less common instruction. That means they are used very, infrequently. Okay, so all instructions have an opcode. Okay, all of them start with an opcode. If you see that there is a opcode first, which talks about what type of instruction it is. Then there are first 6 bits. Okay, first 6 bits. That's all. Okay, this is the way MIPS is encoding the instruction. That's all. Don't worry, you don't have to remember, or I am not expecting you to exactly remember this, but understand how things happen. That's all. Okay, now let us see how the instructions flowing through the pipeline. Now I am going to detail a little bit. Now if you see that I am bringing something new, okay, I will talk about it soon. It is all some registers, hidden registers, and it is called pipeline registers. Okay, they are all, because it is in the pipeline and it is in between 2 stages, there is a pipeline registers. Now you know that an instruction is in any one of these stages, and different hardware is used during those stages, hardware modules. Instruction fetch, instruction decode, and operands read, execution, and effective address computation. Just keep it in mind, it is not only doing execution, it is doing some address calculation also based on the type of the instruction. I will talk about it soon. I will give you an example, and then you will be able to understand. Memory access, it is a data memory access, not a instruction memory. It's a data memory access. Again, this also is based on the instruction and that particular cycle. Write back the result into the destination register. Okay, the goal is to break the instruction execution into sub steps. You know that based on the instruction, some of the steps have to be done. What we are doing in the pipeline is we are dividing into sub steps. Each step or a stage takes 1 clock cycle. We want to make sure it is all the things are done within 1 clock cycle. Why? If one of the stages is taking more than 1 clock cycle, the remaining instruction also will be blocked. You cannot proceed further until the previous one has moved further. So there is a possibility that some instruction may get delayed, but in a normal flow of operation, it should not take more than a cycle. Okay, it is supposed to be taking 1 cycle in each stage. The amount of work done in each cycle or a step or a stage is almost equal. So then only you can move everybody. Suppose 5 of you are moving in a line. If all of you are moving in the same speed, then all of you can move. If suppose a person in the middle is walking slowly than the rest of the people, then what happens? The person in the front may move, but the person behind cannot move. They have to be blocked because the person in front is slowing down. Okay. So if the pipeline has to be effectively used, and if everything is taking only one cycle, then one instruction can come out every cycle. So they have to, each one of them should take same type of amount of work. Okay. The time taken for every stage has to be same. No overlap in the usage of hardware. Okay. Now, one more important thing is, I cannot say that I will access data memory also here and I want to access instruction memory also here. If I say that, what happens? Suppose if I say that during this stage, I want to access data memory as well as instruction memory. In that case, I cannot access the instruction memory during the same cycle because some other instruction is going to be in this stage and it is going to be, yeah, it is called structural hazard. Means I am trying to use the same block in two different places. If I do, I am going to block it because unless I have a provision that it can be accessed simultaneously, I can't do it. So you have to use the hardware blocks here. Only ALU is used only here. Register set is used here as well as here. Okay, there is one difference. I am using the register set in two places. That means what? During the same cycle, okay, in a particular time cycle, one instruction is going to be in this stage, some other instruction is going to be in this stage. Both of them are going to access the register set. How it is resolved, I will talk about it soon with an example. So don't worry about it now. It is allowed and hardware knows it. Other than that, this is only one instruction is using. Only data memory is accessed only in one by only one instruction, and instruction memory is accessed by only one instruction. So there are no hardware block which is in two stages, okay, except this register set, which I will explain. Keep it in mind. I'm going to talk about it. Remember that each stage is working on different instructions on each cycle. You should remember every stage is working on different instruction. Functional units are shared across instructions over different cycle. Now, what is the functional unit? I am talking about ALU is a functional unit. Okay, it is being used across different instructions over different cycles. Okay, in one cycle it will perform an add operation. In the next cycle it will perform an AND operation, and third cycle it may do some other operation. So same block is used for different purposes during different cycles for different instructions, right? Because who is coming in, we don't know. Which instruction is coming in, we don't know. Based on that, it will behave. One exception is that register set is used in both ID stage and then write back stage. ID, what do we do in ID and write back? Let me explain a little bit. In ID, you remember it is for operand read. We are reading the operands. We may read maybe two operands, okay, which is required for ALU to perform operation. So we are reading two operands during the IT stage. We are only reading. And during the write back stage, in the same cycle, the register set used, it is for writing back. That means it is writing the result into the register. So a register write is performed during this for this instruction, and in the same cycle a read operation is done here. Now if you read it properly, during the same cycle, for some instruction here, which is in this stage, two register operands will be read. Similarly, in the same cycle, some instruction is going to be here, which is in the write back stage. Yeah, writing of result is going to happen in the register set. So I told you we cannot have same hardware block used in two stages, but we are using now. Now, how are we resolving it? The thing is, one is for the read purpose and another one is for write purpose. If suppose during the same cycle, if I can do one operation during one half of the cycle and another operation on during the another half of the cycle, I am not doing the same job at the same time. The clock is divided into two stages. First half, this is first half and this is second half. So during the first half, it is shown first here. Okay, this is for the first half, solid line. If you notice clearly, there is a solid line here and dotted line here. Similarly, dotted line here and solid line here. So solid line is coming first. That means during the first half of the cycle, a write operation is performed, and in the second half of the same cycle, for this instruction in this stage, a read operation is performed. So I will give an example and show you today. So keep it in mind, even though we are using the register set in the same cycle on two different stages, we are doing it for different purpose. While this is reading, this is writing, and we are doing it on two different time instances. We are writing into the register set during the first half of the cycle and reading from the register set during the second half of the cycle. As long as it is not happening at the same time, it is allowed. So there is no harm. Okay, as long as the hardware is supporting, the register set should support multiple operands being read simultaneously in one half cycle, and then in another half cycle one result has to be written. Only one result will be written, two results will not be written. So only one result, it is okay. One register write and two register read will be happening on two different half cycles. Okay, fine. And then we are also going to use pipeline registers between the stages. Why? I told you, when an instruction is flowing through the pipeline, whatever instruction fetched is to be decoded here, and whatever is decoded here, it should be processed here. Whatever is processed here, it should be either written into data memory or it should be written into register. So it should be passed on. That means the instruction is flowing from one hardware block to the other hardware block, and during every cycle it is shifted out. So there should be some storage mechanism so that the information gathered here is stored here, so that this cycle it can be used. Similarly, what was here should have been written here so that I can use it during this. So there are some storage elements which are nothing but registers, which are called pipeline registers. Okay, we will talk about it now. Simple structure I am showing you now. This is how an instruction is flowing. I is an instruction, first instruction, which is in this stage, and I plus 1 is read here, whereas I moves here. I plus 1 is here during the next cycle, and then one more cycle I will be here. I plus would have moved here. I plus 2 will be fetched here. So please remember, every cycle, this is the cycle, things are in different places. The instruction I is now here, I plus 1 is moved here, I plus 2 is sitting here, and then I plus 3, when it is fetched, it will be fetched here by the time all of them moves. Okay, so this is how instruction gets moved into the pipeline every cycle. It is like a shifting operation to the right, and during every shift, the results computed, whatever is the outcome of this stage, has to be preserved, which is done in the pipeline registers. Okay, so these are all like a temporary registers which are there. Now I am going to ask you one question here. Okay, during which cycle the pipeline is full? When I say pipeline is full, all the stages are busy with some instruction. Assuming I is the first instruction after reset, that means I am assuming I, when it came, there was no instruction here. In these stages, no instruction was there. On reset, everything is reset, all pipeline, everything is reset. First instruction is read, it is coming here, and these blocks are doing nothing. Okay, I am going to ask you a question. In which cycle the pipeline is full? That means every stage is having one instruction to process. So a quick poll, it should not take more than 10 seconds. Okay, more than 10 seconds. Please quickly answer. I am not going to wait more than 10 seconds. Already 10 seconds over. Only 6 responded, but all of them are correct. Okay. Let me not wait for long because we are losing time in waiting for the poll. So let me share the result. I'm still surprised that you guys are thinking it is BCD. Okay. I have minimized it. Let me see whether I'm not able to see it now. It went off. When I minimized it, gone. Okay, let it go. I hope you can see the screen. Let me erase everything. See, I told you the first instruction is this, and there are no instructions here to start with. After that, it will start moving in. When will the pipe be full? Only when this I moves here. When I moves here, how many cycles have gone? 5 cycles have gone. CC5, I will be here. When I is here, I plus 1 would have moved here. Assuming that no instruction is getting stalled or stopped. I plus 2 will be here. I plus 3 will be in this stage. I plus 4 will be in this stage. That means every block is busy with some instruction, which will happen only when CC5 is there. No, during this cycle only, all the stages are doing something busy. Okay, busy with something. So the correct answer is CC5. Okay. Let me erase it. Okay. This is called a steady state, and it is the full pipeline. The pipeline is full. Afterwards, what happens after that? After the CC6, CC7, if suppose instructions keep coming and they all get executed without any delay, you will have always pipeline is full. Only in the beginning, when on the reset maybe, or some other reason, I will tell you later, the pipeline will be empty and you are refreshing the pipeline with new instruction. Okay. When your code is jumping to some new location, then the pipeline has to be flushed. When you say pipeline is flushed, all the instruction in the pipeline is removed. Okay. So when the flushing of pipeline happens, all the stages will be empty except the first one, which is getting fetched. After that, it will start moving in and you will start seeing that different instruction come into the different stages. So you should be able to understand this picture, which is very important for you to understand the remaining topics. Okay. Now, during this cycle, as I told you, register write may happen. Okay. And during this time, right, register read is happening. Now, why they have designed it like this? Why not the other way? It could have been done in the other way also. The reason is, if any instruction is writing the result which is required for this instruction, we can do it, we can get it, because it will write into the register now, and in the next cycle it can be read. So you can get the value here easily. That is the reason. If you don't understand my explanation, don't worry. I will come with the show an example and then make it clear. Okay. Now I am not going to take more time here. This is how we show it. Different instruction in different stages. This is a normal way picture is shown. Each pipeline stage takes a cycle to process in an instruction pipeline. The above picture shows the typical way a pipeline structure is drawn. Maximum of 5 instructions can be in the pipeline, which is a steady state at different stages of execution. We have only 5 stages here, so it is 5 instruction. If there are more stages, there will be more instruction. Now, one more quick quiz. I'm not going to poll now. You just answer, keep it in a mind, write it on a paper. The clock number at which the completion of instruction execution of I happens. When is the instruction I getting completed? Which clock number? Okay. I hope you have the answer now on your paper. 5. It will be completed maybe after 5, you can say, or if you have said 6, assuming that because during the 5 it is not happening, it's okay. At 5 it will be done. Okay, after 5 completed, the instruction, this instruction is completed. The clock number at which the completion of instruction execution of I plus 3 happens. When is the I plus 3 happens? You can see when the WB is here and which clock number, you can see the answer. It is very trivial. I hope it is clear to you why I am saying that actual completion formally happens when the instruction is going out of the pipeline. This instruction I will be out of the pipeline after 5. Okay, so it is completed. Now I'm going to talk about pipeline registers. Okay, and then what is synchronous pipeline? Let me first talk about synchronous pipeline. Synchronous, you all understand that every stage is going in a lockstep. Lockstep means they're all synchronized on a single clock. This is the clock. Now I want to know what is the clock duration I should give. What is the duration of the clock I should choose? Now it is based on the logic circuits. See, these are all combinational circuits. Some AND gate, OR gate, some adder, subtractor, something. Okay, built on based on some logic circuit. It's a combinational logic circuit. So there is no memory element here. Okay, memory element is here. That means any flip flop. If you remember, flip flops, D flip flops, JK flip flop, all that we have studied, they are all used for registers. They will be able to hold the value during this. Okay, these are the hardware components which can store the value. Whereas these logical circuits, based on the input, it will give some output. Okay. Now imagine that I have too many AND gates. Okay, connected like this. If you remember my digital design course, every gate has a delay. Okay, when you give some input, it will take some microsecond, nanosecond for the output to appear. So if I have too many logic gates for my circuit, suppose instruction decode is very complex, I have too many levels of logic gate. When I give an input and the time I get an output is what is the maximum time taken by this stage. I call this as a tau 2, the time taken for this combinational circuit to respond to any input given. If I change the input here, I should see the output response by that input passing through all these gates and appearing here. So if I have too many gates, my delay will be more. So the time taken by each of those stages will be different. Okay, it depends on what logic is inside. Assume that there are tau 1, tau 2, tau 3 and tau 4, tau 5. Now, let us now look at what should I be choosing the clock. I am asking a question now. Have an answer in your mind, and then when I explain, you will be able to see whether you are correct or wrong. Now, suppose if I say tau 1 is greater than tau 2, tau 2 is greater than tau 3, and tau 3 is greater than tau 4, and tau 4 is greater than tau 5. That means what? I am giving a comparison, assuming that tau 5 is the smallest value and tau 1 is the highest value. That means the logic circuit, whatever is here, is taking more time than any of those stages. Assume. Now, I have a requirement. I want this whole pipeline to be synchronous. That means I should be in a position to move one instruction from here to here, and then at the same time they should move from each stage. Okay, same time. If that is the requirement, I should decide the clock. Okay, I should decide the clock taking time. Okay, some time t. Okay, should the t be equal to, should the t be equal to tau 1, or should the t be equal to tau 5? This is the smallest number I said, and this is the largest number I said. it is going to be taking more time instruction fetch because I assume some reason. So because of some reason, okay. It is not that always it is going to be like this. I am giving an example. It could be anything, can be smaller, okay, or larger. Assuming that tau 1 is the largest number, the delay, and tau 5 is the smallest delay, should I give the clock equal to tau 1 or tau 5? Why I have to decide one of them? Because I want everybody to move in the same sequence so that I get the stages are moving in the same sequence. So any of you thinking about some answer, you can chat on a private chat and share it with me so that I know that. Okay, I got some answer. Very good. Okay. So I will not reveal who is giving what answer. Let me tell you how to think. It is like this. Suppose this is the movement, okay, movement of people. Suppose these are all in, these are all blocks, hardware blocks, which are taking different time to process an instruction, and then they have to move through the stages. Now, if you recall the weakest link I talk about, weakest link, that means if there is a chain and if there is one chain which is the weakest, the even if other strings are, loops are very strong, the weakest link will be deciding the strength of the chain. Similarly, the delay, the longest delay or the smallest delay is going to influence your decision. See, our requirement is that this pipeline should move in lockstep. Lockstep means they should all move in coherently. They should go across. Then, if I can make the fastest fellow to slow down, okay, but I cannot make the slower person to walk fast. Okay, I can't push. If I push, what happens? It will be that fellow will fall down, and then I have to take the person to hospital. In this case, in the hardware logic, if suppose a particular stage is taking more time, and if I say that no, I can't wait, you are taking more time, I have to just go, I will change the clock. Then what will happen? Let me explain that. What is the impact of that? Suppose this is taking more time, I said, and there is a logic circuit which is taking more time. For an input what I gave, the output is taking tau 1, which is a longer time. But I decide that I am going to change the clock to tau 5. I am going to fix the clock to tau 5. Faster. I am going to make it fast. Then the instruction fetch wouldn't have been completed. It may be halfway through. The stage of the FIFO, the logic circuit or the content which has been read from the memory will be in a indeterminate state, indefinite state, or unstable state. If I change the clock, I am going to latch whatever value here into this pipeline register, assuming that this is the result of this stage. If I don't give the actual time taken by the stage, I am going to get a wrong answer. This particular logic, whatever the logic is here, it is not going to give me the correct answer because I am latching the value which is unstable or which is incomplete. So the whole execution will be wrong. Now, what if I give more time? Suppose there is too many logic circuits here. I give an input, some output is waiting here at the output. It has completed the work. The influence of this input has come out here. But I am not latching now. I am latching after some delay. There is no harm because the value, whatever I have given, is I got the result now, which is some state, 1 or 0. Once it has come here, which is in a stable state, I can latch this value either here or maybe later, doesn't matter. I can delay, okay? But I can't do it before. It is like this, when the food is getting cooked, if the food is fully cooked, okay, at this time, you can eat anytime here, but you cannot eat the food which is half cooked. And then I cannot say that I want to eat now. It will be, indigestion will happen. So it is similar to that. I can take the output after the time, the maximum time a particular stage takes, I can latch it. It will be stable and correct, but not before. So in that case, I should wait for the longest stage to complete its operation. The stage which is taking more time, I should wait that long. Then the clock I should decide based on tau 1. If I wait for tau 1, then this result is available because it is the maximum. It will be available. I can latch it, and tau 2 is smaller than that. It would have been ready even before this. So I can latch it now. So all the results are valid now. So if I wait for the maximum delay, I can comfortably say the pipeline is working fine. So let me now, I think the synchronous pipeline I explained now. Let me say how these pipeline registers are named. This is IF stage and this is ID stage. It is named as IF/ID. This is the register. This pipeline register is called ID/IEX. This is EX/MM. You know what is the name of this, okay? EX/EWB. So each of the registers are having some name. It is for our discussion. Do not think that it will be used for any programming. You cannot say move IX, comma, slash ID, comma R1. I cannot use this as a part of instruction. It is not visible. These instructions are not visible for a programmer. Only those what are there in the register set, flags, those registers are available, but not these internal hidden registers. There are so many hidden registers in the processor which is not known to us, which cannot be accessed by us. We can only feel the performance, or we can understand what is the job it is doing. That's all. Okay. So these are all called pipeline register. Pipeline registers pass the values of results across the stages. Also control signal. It is also passing the control signal, because what is the instruction fetched should be passed across, so that when it is write back is happening, you know that whether it is add R1 comma something or R3 comma something, so that it can perform that job here. So whatever is understood by the instruction has to be passed. So control signals are also passed along with the some values. What is computed in that particular stage is passed to this registers. Okay. Every stage behaves differently based on the control signal generated in the ID stage. Pipeline registers are hidden registers, not visible and accessible to programmers. I explained to you. Okay. I have explained the pipeline register now. Let me talk about something which I spoke about tau 1. All of you are aware that new instruction is issued every clock cycle. On every clock cycle, the results of each stage moves into the pipeline for the next stage to consume. So the pipeline clock duration tau is max of tau while. I have to choose the maximum of this, which I explained some time back, as a clock duration. Once this is fixed, whatever may be the delay taken, all of them are moving with this tau 1 speed. Okay. So if they all have to make a progress, the slowest module decides the speed of the whole module. Even if they are all finishing it fast, they have to wait for the slowest one. Okay, that is the reason. So this is what I said. So slowest stage is this, so we have to choose that. The reason is that all stages need to work in lockstep. They have to, lockstep means they have to move in coherent, synchronously. Okay. Okay. Now I will complete. We have 2 more slides before I stop. Although many figures will omit such registers, okay, normally you will not see them. Okay. For simplicity purpose, they are all required to make the pipeline operate properly, and they should be present. Of course, similar registers would be needed even in a multi-cycle data path. Okay. I'll explain to you. Had no pipelining, because only values in registers are preserved across clock boundaries. See, if suppose you saw that CPU, unpipelined CPU, which is taking multiple cycles to go across, you found that there was some register called MAR, MDR, sorry, my handwriting is bad. You saw some registers used. They are all required for storing some values. Remember, a combinational circuit cannot store the value. Only flip-flops can store the value. So you need registers which are constructed using flip-flop to store the value across the clock boundaries. So when I say clock boundary means between two clock cycles, the values are preserved only in the flip-flops, not on the combinational circuit. Combinational circuits just behaves like based on the input, it gives output. It doesn't store. There is no storage element in the combinational circuits. Combinational circuits means some combination of AND and OR gate together constructed. Okay. I'm just going back into digital design. So in the case of pipelined processor, the pipeline registers only also play a key role of carrying intermediate results. So whatever is the result, it is carrying it. Okay. That is the job of those pipeline registers which are appearing between the different stages. For example, a registered value to be stored during the store instruction. Suppose if I am executing a store instruction, I found that I have to store a value R1 into the memory. Now R1 is accessed here and actual storing is happening in the memory at this cycle after 2 cycle. Now unless I pass the value of R1 through this pipeline registers, I cannot perform a write operation on data memory by giving the value. Remember, when you are writing into data memory, I have to tell which value to be written. That I picked up in the stage which is farther ahead. 2 cycles before I picked up the value. I want to store it. Now this is R. Now suppose in this case R6. R6 values to be stored. Now if I have to store R6, I picked up R6. This is an operand. I picked up this when this instruction was executed here. Okay, when instruction was passing through. Okay, when I say execution means the store instruction is passing through different stages. It is passing through this also as well as this and this. Now when it is passing through the ID stage, R6 is picked up. Okay, and then actual storing is happening during the data memory access. That time this value is stored in the data memory. So I need to pass that value through this data, this pipeline registers. Okay, that is the job of pipeline. Understand it well. It is very, very important to further go into the detail of pipeline. Likewise, suppose I am executing this instruction add R1, R2, R3. I am fetching R2 and R3 here. I am adding it here. After adding, I am writing the result in this stage, which is written into R1 here. Until if I have a result here, which is to be written into register, I should store it in pipeline and then I should pass it across pipeline. So apart from whatever you see here, there is some direct connection between pipeline to pipeline register, which is passed across. Okay. So I'm just explaining you the purpose of pipeline registers and what it is doing. It is passing the values, passing across the pipeline. It is directly connected, which is not shown in the picture. Okay. So it is sometimes useful to name them, which is named already. Okay, we know this already. Okay, one more. Okay, now how much time elapsed? Already 1 hour over. Should I stop here or show you one instruction and then stop? I will only demonstrate one instruction. Okay, and then stop so that you get some idea. Okay, just give me. I was supposed to give you a break here. Okay. Okay, somebody is telling me something. Okay, no, please. I thought some yes, I'll get. One instruction, guys, I will repeat again tomorrow, but it will make you at least understand. Okay, add R1, R2, R3. Let me just tell you. Oh, crying babies. Okay, I will stop. If you guys are crying, I will stop. Okay. Let us continue from here tomorrow. We are going very slow. Okay. But I don't want to hurry up if you don't follow. So tomorrow what I will do, I will not do a quiz tomorrow because it is taking more time than required. So I will start off from explaining this because this itself is like a quiz. So we will start discussing something from the time we join. So please don't be late. Come on time. Otherwise it will be difficult. Okay, guys. I hope so far is you followed. So see you tomorrow